Welcome, everyone. Today, we are diving into a really fascinating explainer. We're unpacking a highly complex paper that, quite frankly, completely rethinks how we measure, well, pretty much everything. Our main goal today is to uncover this unified geometric framework that actually lets us compare completely unrelated variables. We are talking about finding a legitimate, solid mathematical bridge between things that, on the surface, seem entirely incompatible. It's like finding a way to mathematically compare apples and oranges.
Okay, let's dive right into our roadmap for today. First, we'll look at the problem of comparison. Second, the mean squared error trap. Third, the 0-to-1 solution. Fourth, temperature versus wealth. And finally, we'll wrap up with the right triangle manifold.
Section 1. The problem of comparison.
So let me ask you this. To put it bluntly, how do you mathematically compare a temperature reading to a bank account balance? Seriously, think about it for a second. They operate across completely different dimensions, totally different units. Honestly, it sounds like the setup to a bad joke. But structurally, finding a way to map these heterogeneous data sets onto a single comparative axis is a massive mathematical hurdle.
Moving on to Section 2, the mean squared error trap and contraction bias.
So why can't we just compare them using the math we already have? Well, the issue lies in something called mean squared error, or MSE, contraction bias. In standard systems that are literally designed to minimize MSE, the statistical quantizers, the tools we use to measure and group data, they actually suffer from a systemic flaw. They systematically pull extreme data points toward the origin point of 0. By mathematically trying to average things out, they end up completely distorting the true relationships of those near-zero values.
So the crucial point here is that this contraction bias literally erases a data point's haseity. Now, that's a beautiful term borrowed from the philosopher John Duns Scotus. It translates to a thing's thisness, or its unique identity. When traditional averages forcefully pull everything toward 0, we lose the exact individual signature of the data. It leaves us with a mathematically flawed comparison that just doesn't respect the data's true, unique shape.
Section 3. The 0-to-1 solution.
Okay, let's compare the old way of doing things with this brilliant new way. Standard mathematical formulations define what are called metallic means, using pure continued fractions. The problem? These are anchored to specific integers, meaning their value is always greater than or equal to 1. But to compare our completely heterogeneous variables, the author implements a novel data normalization transformation called the fractional continued shift. By forcing that leading integer term to 0, this new coordinate becomes strictly bounded within the unit interval. It always sits neatly between 0 and 1. This essentially levels the playing field for absolutely any dataset, giving us a totally dimensionless metric.
Section 4. Temperature versus wealth. Let's actually see this in action, because this is where it gets really cool. This is how we mathematically compare the weather outside to your bank account. Step 1. Imagine a physical system recording a thermodynamic temperature of 300 Kelvin, bounded between 200 and 400 Kelvin. If you normalize that, it puts 300 exactly halfway, right? Giving us a fractional state of 0.500. Step 2. Now take an economic network and normalize a median wealth index. Guess what? This also yields a fractional coordinate of 0.500. Step 3. By converting these wildly heterogeneous physical and socioeconomic variables into fractional shifts that are strictly bounded between 0 and 1, we completely bypass that MSE contraction bias we talked about earlier. Both thermal energy and economic wealth literally yield the exact same fractional coordinate.
And when you solve that inverse decay equation, it maps both of them directly to this specific coordinate index, m equals 1.5. In the language of geometry, this translates to a parameter b of exactly 3/4. Just think about how incredible that is for a second. Physics and socioeconomics have just been pinned to a single, elegant number without any of the systemic contraction bias that normally ruins these types of comparisons. And this brilliantly illustrates the geometry behind it. Notice the exact 4, 3, 5 Pythagorean right triangle configuration. Our horizontal base A is locked to 1, and our vertical parameter B is exactly 3/4. This literally physicalizes that abstract fractional shift we just did right onto a concrete geometric continuum.
Section 5. The right triangle manifold.
So to make this work seamlessly across literally any possible dataset you could throw at it, the framework applies Thales' theorem. If you remember from geometry, Thales' theorem proves that any point along a semicircular boundary naturally satisfies the right triangle condition.
So instead of being stuck with clunky, discrete integer jumps that create massive blind spots in our data, Thales' theorem maps our indices onto a smooth, continuous right triangle manifold. It allows our parameter to just slide smoothly along a continuous semicircular spectrum without a single geometric gap.
So what does this all mean? If we summarize the sheer magnitude of this achievement, we now have a scale-invariant, cross-domain reference frame. By stretching the data over this continuous right triangle manifold, fields as completely disparate as physics, biology, and economics can finally speak the exact same mathematical language on a unified axis. It's a total game changer.
Which leaves us with a pretty staggering implication, doesn't it? If a perfectly unified geometry can seamlessly bridge the gap between thermodynamic heat and a bank account without losing the unique identity of either, what other fundamental connections in our universe are just waiting to be mapped? I really hope this explainer has completely shifted how you view the geometry of the data all around you. Thank you so much for exploring this with me today.